I would like to introduce today our new modeling approach, high-throughput super-resolution single-particle trajectory analysis to reconstruct organelle dynamics and membrane reorganization. So this work has been published in lReport method, and it is associated with the ImageJ plugin called SPTanalysis. And today I would like to summarize the different parts of the algorithm that can be used. So the SPTanalysis plugin is a pipeline that uses trajectories recorded from SPTPalm once they have been connected by a trackmate so that you start with a trajectory. Then, using a discretization both in time and space, using the images, we can give a binarization, and with this binarization we use a modeling approach to estimate information of interest coming from the Langevin equation, where the velocity is given by a drift of force plus a diffusion map. So the result is a high-resolution map given by the density, the drift, the diffusion, and the displacement maps. The algorithm we have developed allows to detect automatically regions of high density, such as potential wells, and obtain information about their position and their geometrical localization, as well as the energy. Finally, it can be used to reconstruct a network such as the endoplasmic reticulum network. The output of the algorithm allows to estimate the statistics, any statistics of interest, and to explore, to see how the space can be locally explored by trajectories. So now I would like to go in the details of this analysis. So this is an example of calcium voltage channel that fill the neuron, and you can see the trajectory passes through many points. Each color corresponds to a trajectory. So over the past 10 years, these methods have been generalized and has found many applications, such as this example of trajectory recorded on the HIV viral protein GAG, on AMPA receptors moving on the surface of neuronal cells, calcium voltage channels moving on the surface of axons, or the careticulin moving inside the surface of the ER lumen. In all these cases, we can see that the distribution is not homogeneous but characterized by a region of high densities. Another example is at the neuromuscular junction of the Drosophila, where you can see that most of the trajectories are located inside this region of high density, highlighted with these red ellipses. So this nanodomain corresponds to the region of high density revealed by this SPT. So now how to analyze this region? Starting from the ensemble of trajectories, it is possible to calculate the density map, the diffusion map, and also the drift map. So the same is possible not only on the surface of a neuronal cell on the membrane, but also on this network, such as the endoplasmic reticulum, characterized by tubule here in red and through a junction in blue. So the ER organization revealed by the SPT, so this is an example here where you see trajectories recorded on the endoplasmic reticulum, and by changing the color code, you can see that region of high density are associated with low velocity, whereas region of high velocity are trajectories that move in between these low velocity regions. The present algorithm allows to start from trajectory, to extract the density map, compute the diffusion map, and also reconstruct the underlying network, where trajectories allow us to estimate the flux in between two different nodes, and so we can characterize them as either unidirectional or bidirectional if there is enough trajectory that moves in both directions. So over the last 10 years and more, there have been an increasing number of work using based on single particle tracking, showing the need of having a software and the methods to analyze them. So what to extract from these single particle trajectories? We can use the Langevin theory as a physical framework to extract these parameters. Starting from Newton's second law of motion, m acceleration equals force. And Langevin proposed to add a friction term and the Brownian collision to have a better description of the motion of a particle. So in the large friction limit, gamma large, this equation reduces to this one, which is called the Smoluchowski limit, where the velocity is basically given by the force plus these Brownian terms. The first one is calculated from the first moment of statistics, and the second one by the second moments. Now we have a reverse engineering problem, and the question is how to reconstruct the forces from the trajectories. So starting from the Smoluchowski equation, the question is how to reconstruct F and the diffusion coefficient. So a discretization of the equation is given by this, where delta x is called the displacement. So the reverse engineering problem has been solved using these two estimators, where the field B is the expectation of the displacement condition at x of t equals x, where the diffusion coefficient is the same, but using the second moment. So the conclusion is that we have an arbitrary small delta t, which is not delta t tends to 0. We need a large amount of overlapping trajectories. This method only requires 2 successive points, but not the entire trajectory. And this method cannot be substituted by looking at averaging over a long single trajectory. So the estimation of the drift is done in the following way, using an images which is binarized with bean of size delta x. We look at point falling in each bean, calculate a time t and time t plus delta t. So we obtain this instantaneous vector, we obtain the average, and this gives the estimator of the field in a given bean. And the diffusion tensor is calculated similarly with using here this second moment. Now this method can be improved, but instead of calculating everything on a bean, we can use a sliding window which will increase the resolution and by multiplying by a weight function. So the previous estimator becomes the following estimator, which are weighted by this cosine function. This increases the accuracy, as shown here. This is classical calcium voltage trajectories. This is the raw map, and this is a cosine filter map. And from here, it can be seen that we increase largely the resolution, as shown here. It's in this magnification. Instead of having this binarization, which is very apparent, you can see how smooth is now the final calculations. So now let's discuss the origin of this high density region. They are usually coming from the field of force, could be conservative. In that case, the force is minus the gradient of a potential, and when it is the case, the density is associated with this potential that is in first order approximated as a truncated parabola. So this truncated parabola, this represents in dimension 1, can be seen here in dimension 2, or using the gradient characterized by these converging arrows. It is characterized by 5 parameters, 2 for the center, 2 for the different sizes A and B, and 1 for the energy. So applying this concept on trajectory recorded on single particle trajectory over 3 cell population, you can see here that the algorithm allows to detect automatically this region, red ellipses, and calculate the density map, the diffusion map, the drift map, and all statistics of interest. In addition, the converging arrows confirm the fact that we have here potential wells to characterize this region of high densities. So the algorithm can also be used to recover the boundary, and we have 3 different algorithms. One is associated to the density of point, and using 2 different thresholds, it is possible to recover the boundary. The boundary is characterized by a change in the nature of motion from Ornstein-Uhlenbeck type process to Brownian motion. Another possibility is to use a vector field, where inside the potential well we have converging vector field, while outside the direction is random. Finally, we can use a third method based on the maximum likelihood estimator by the minimization of this a posteriori probability for the motion, the transition motion. We can estimate the information coming from the drift A and mu, and coming from the diffusion coefficient D. So the network reconstruction procedure uses the fact that low density region, high density region are characterized by low velocity, as shown here by the reconstruction of the ellipses in white, and while the tubule extraction is possible by using the fast velocity, leading here to the connection between the different nodes. So in the end, the algorithm allows to reconstruct the position of the node as well as the connectivity C. So thank you for your attention. Any feedback on the plugin are welcomes, and I'll leave you here with our email address. Thank you for your attention.